In this video, we will be learning about unsaturated hydrocarbons, which are known as alkenes and alkynes, and learn to draw their structures. So alkanes had single bonds between carbon atoms. Alkenes have a double bond between carbon atoms. Double bonds are where 4 electrons are shared. Alkynes have 6 electrons shared between carbon atoms. Alkenes and alkynes are everywhere. Lycopene, which is responsible for the red color in tomatoes, gets its color from the alternating double and single bonds in this molecule. These are conjugated double bonds is what it's called. So there's 13 double bonds in this structure. Acetylene, which is used for welding torches, is more properly named ethine, but no one calls it ethine. It's used for welding. And then there's a fun class of molecules known as nanoputanes, which are which are shaped like humans, and they've tried to put hats on them and make them in different poses and stuff. So nanoputanes are organic molecules whose structures resemble human forms. Alkanes, we said, were saturated hydrocarbons. Alkanes are saturated with hydrogen, meaning they have the maximum number of hydrogens possible for the number of carbons present. That gives them a generic chemical formula of Cn, and then the number of H's is twice the number of carbons plus 2. Alkenes and alkynes are unsaturated hydrocarbons, meaning they do not have the maximum number of hydrogens. Alkenes, their generic chemical formula is Cn with twice as many hydrogens. That's assuming one double bond. For each double bond you have, you will be removing 2 hydrogens from the structure, sorry. So here you can see that this alkene is just 2N, and this is plus 2, so we subtracted 2 hydrogens. For an alkyne, which has a triple bond, we're subtracting 2 more hydrogens from the structure. And so that's assuming 1 triple bond. If you have more than 1 triple bond or more than 1 double bond in the structure, you would have to subtract 2 electrons from that formula in order to figure out how many hydrogens are present. If you look on nutrition fat labels, this label of saturated is listed on nutrition fact labels. So saturated fat has the maximum number of hydrogens present on the chain of the lipid. When we have our fat lipid chapter, we will talk about the chemical structure of fat and the structure of saturated fat and trans fat. But it has to do with alkanes, alkenes, and alkynes. Well, not alkynes, those aren't in fat, but alkanes and alkenes. So what is the molecular geometry around each carbon atom in this alkene? Go ahead and pause the video and try to work out and remember what these are. Unpause the video when you are ready to answer these questions. Okay, so in this alkene, there are 1, 2, 3 electron groups around each carbon. So each carbon is a trigonal planar geometry. In a trigonal planar geometry, the bond angles are 120 degrees. You can remember this because a circle has 360 degrees. And so if you divide that into 3 pieces, then you end up with 120 degrees. What is the molecular geometry around each alkyne? Each alkyne has 2 electron groups, which means it is linear. And the bond angle for linear is 180 degrees. That is like a circle cut in half. We care about the bond angles and geometry because that has an effect on the overall geometry of our molecule. When you do draw the condensed structural formulas for alkenes and alkynes, you are allowed to flatten the molecule to some degree, unless there's isomers present, and we'll talk about isomers shortly. But you can see that this would also count pretty much as a condensed structural formula with the CH3 right here. But you always have to draw the double bond. That's what's really important here. You can't omit the single bonds between the carbon and the hydrogen so that it's more condensed. And then when you draw the line structures for it, alkynes, you have to remember that there's a carbon there, and then based on the spacing, there's also carbons present on either end of where that triple bond is. But alkynes are drawn linear because that is a 180-degree bond angle. So you just have to make sure that you are counting those two carbons in the line structure. A line structure for this alkene would simply look like that because there's 1, 2, 3 carbons total. So you have 1, 2, 3, and that's a methyl group, and then that's the double bond in between. And we don't draw hydrogens.